The topic of this video is the independent means t-test. Based on the in-class exercise, do students perform math at a different rate when an incentive is offered? Students were randomly divided into two groups. In sample 1, the first group was given a times table paper and asked to complete as many squares as possible in 2 minutes. These students comprised the ordinary group. In sample 2, the second group was given a times table paper and asked to complete as many squares as possible in 2 minutes. However, they were also offered a monetary incentive. If anyone in the second group could complete more squares than the instructor, that individual would receive a calculator worth about $100 and $30 cash. These students comprised the incentive group. Look at that research question again. Do students perform math at a different rate when an incentive is offered? Remember, we do research on samples in order to be able to say something about populations or entire groups of interest. So what descriptives do we have? We have sample means and standard deviations. The dependent variable is scores, representing the number of squares completed in the 2-minute time frame. And what are we testing for? We're looking for a significant difference between sample means, not just a difference between the means. Continuing that thought, people are different. Surely we cannot expect two samples to have identical means in this thing. There's some difference that's accounted for by chance factors. Is the difference between means statistically significant, though? Can we say that the observed difference exceeds what can be accounted for by chance? That is what we're trying to figure out. In class, the ordinary group had a mean of around 68 squares completed, and the incentive group had a mean of around 64 squares completed. The difference between means was about 4, with the ordinary group completing more squares than the incentive group. And I'm rounding off for this discussion. So the question is a difference between means of 4 in this situation meaningful? We found that the difference between means was not statistically significant, which means that from this study, we can answer the yes-no question of significance. Do students perform math at a different rate when an incentive is offered? With no, they do not. You can see the SPSS output here. But whether the incentive made a difference in performance or not, there's no reason to think the variance would differ. It's not like being given an incentive suddenly makes students more different from one another, like suddenly there's some bigger variance, or that they're now more similar to one another. Students are just as much different from one another. Some are quick at this, some are tired on this particular day, some don't care, whatever. Picture a normal curve. That's the assumed shape of the distribution of scores for the entire population of interest, all students. If the incentive impacts performance for real, then the graph is shifted to the right or left for all students' performance with an incentive offered, because the mean would be higher or lower from the incentive. That's the hypothesis. The potentially significant result is a difference between means. And here's where this exercise frustrates me a little bit. On the one hand, I love this in-class exercise because I actually know how it's going to turn out. Based on having done this in many classes over the course of teaching at 2 different schools for about 10 years, every single time I run this little test, the incentive group does a little worse than the ordinary group. Every time. The difference between means varies a bit, but the incentive group always does worse. And from this, I feel pretty confident in saying that in reality, the incentive impacts performance, at least in the conditions in which I offer it in my classes. And that is an effect. And yet, this is what frustrates me. I have never gotten a statistically significant test out of this. And check that out, because this is important. I've done this test probably 100 times. In classes with students of different ages, every single time the incentive group does a little worse. And yet not once have I ever gotten a significant test statistic. The difference between means is never good enough. See that SPSS output and look at the p-value. The p-value is the probability of getting that sample score if the null hypothesis is true. As you can see, statistically speaking, the probability of this difference between means of 4 squares is pretty high. Statistically, this observed difference between sample means is nothing special at all. Here's what that p-value is telling me. If I had my first sample of 9 students complete the test under ordinary conditions, and then I had my second sample of 9 students also complete the test under ordinary conditions, all right, so if I had my 2 samples do the same exact thing, never mind the incentive, I might very well see a difference between means of 4 squares. That's what this p-value tells me, and that's my problem here. My difference between means, when I only have 8 or 9 people in each sample, is completely normal and ordinary. There's no way I can give any credit to the independent variable, which made my 2 samples different, my incentive. Why is my difference between means never good enough? Here's why. This test lacks statistical power. Power is a probability, some number between 0 and 1, and it tells me the likelihood that I'll get a significant result when the null hypothesis is false. It considers both effect size and sample size. So power tells me the probability that my study here will be statistically significant, because I know that this incentive matters. From what people tell me, it's probably the pressure or the stress of being surprised to learn that in 2 minutes you can earn about $130 in technology and cash. But whatever the nature of the why, I do always see the incentive group performing worse. And the probability that I will ever see that statistically significant result is pretty small. And this is because my samples are so small. Considering what's in this power table, should I honestly walk away from this exercise thinking the incentive does not influence performance just because I did not get a significant statistic? I don't think so. I can, however, suspect that the effect is not large, given that I have never found statistical significance. But check this out. If I got 100 students to 2 groups and ran this test, I'd get my significant result, at least sometimes. And that's because the difference between means does not have to be all that much if I have a bigger sample. My standard error would be smaller, n is in the denominator of that fraction. Sample size helps determine statistical power. And so does predicted effect size and significance level, but in this exercise, it's about having sample sizes that are simply too small. And if I have here a small effect, and if you could help me get like a few hundred students together for this, I could expect to get my statistically significant test 4 out of 5 times, given the above table, showing the necessary sample sizes for 80% power. So we could do this if we got a bunch of people together. Take a look in the assigned textbook reading again for the logic of effect size and statistical power, paying particular attention to where the sample size comes into the picture. I am getting a type 2 decision error in this exercise. I could reduce the risk of this error by increasing statistical power. And I could increase power by having more people complete the task. Beta is the risk of a type 2 decision error. It is literally the opposite of power. Think about it. I've incorporated a lot of fundamental concepts into this discussion. Hopefully, because you personally participated in it, the logic makes some sense at this point.